Hi and Assalamualaikum. Today I want to explain this question about the E-MOSFET drain feedback. Okay, this question asks you to find VGSQ and GM, and then AV, Vout, finally Vout when Vin equal to 4 millivolt. Okay, even though I don't mention that this is a drain feedback configuration, you must know just by viewing at this. So this is the RF. Okay, so any circuit that has RF, then we call it a drain feedback. And this is the E-MOSFET that used in this circuit. So we take a look the information that give to solve this question is ID on, VGS on, YOS, and VGS TH. Okay, so to get answer for A, question A, VGSQ, we use DC analysis. Okay, then GM is AC analysis. For the AV until Vout, all are AC analysis. But for this question B, you are not only calculate the voltage gain value, but you have to derive it. Derive from the circuit. Okay, let's take a look the question A. So to get VGSQ, you need to find from two equations. The first equation is from the device. This device in this question is E-MOSFET. So remember that E-MOSFET, it has its own equation, which is ID equal to K multiply VGSQ minus VT squared. Okay. The information given here, there is no K inside this. No K value. So you need to calculate K first. Okay. Here. Find K first. Okay, K, the formula is ID on divided by VGS on minus VTH squared. Then when you insert all values, you get K equal to 0.44. Okay, then insert this value here, you get the equation 1. Okay, next we go to the second equation, which is the network. So network is drain feedback. Okay, drain feedback. When I say the drain feedback, okay, for this one, you need to do the DC equivalent circuit. Okay, you transform the original circuit to DC equivalent circuit. Okay, now for the DC, remember that RF value is always large. Okay, the value is normally in mega ohm. So what happened during this, the DC time, this RF is gonna be a short circuit like this. So you have to draw short circuit here. RF already gone. Only that. And then you transform this DC value into this kind of you see, this is the original circuit. You have this symbol for the DC 20 volt. Then you change to to be like this. So this is the final circuit for the DC equivalent circuit. Okay, then we need to find VGS. For every time when I say about the equation of the network, it means VGS. We want to find VGS. So where is the VGS in this circuit? Here is VGS. Okay, so you have VGS here. Okay, this circuit, because of this wire, okay, when this wire has shortened the circuit, it become VG from here, VG equal to VD. Because there is no resistor on here, no resistor, then VG value equal to VD. Okay, VG equal to VD, then we get this one. And at the same time, the VS here is 0. So when I do the equation VGS, this is the basic equation that I always mention in class. VGS equal to VG minus VS. Then we know that VG is same with the VD, so VGS equal to VDS. Okay, then we know that S equal to 0, therefore VGS equal to VD. And what is the VD? Okay, this is VD. VD equal to VDD minus IDRD. How we get that? Okay, this is VD. I do this loop from here to here. Okay, so negative here, negative VDD, okay, plus IDRD plus VD equal to 0, then you get VD equal to VDD minus IDRD. Okay, here the equation. So now I get these two equations. Then we substitute equation number 2 into 1. Okay, means that from the ID equation we can get the VGSQ. So I insert the VGSQ here. So this is VGSQ. Okay, this is the VGS inside this. Then you expand this equation. Be careful with the mathematics. Okay, be careful with your calculation. You have to do it very clearly. So 20 minus 10k, ID minus 4, and I get this. Then when I expand, because this is the squared, so this is my calculation. Then I get, when I get this equation, multiply with k, so I get this value. Okay, remember that this equation is equal with ID, and here is ID, and here is ID squared. Okay, then we make this equation become balanced. We set 0 here, so transfer this ID to here. That's why we get ID negative 142.08 ID minus with 1 ID. So it become here negative 143.08 ID. Then this equation be equal to 0. Okay, remember that this is the final equation for the quadratic equation. Okay, then you have to solve using this formula. Okay, remember that here there is a negative, and this is a b squared minus 4ac divided by 2a. Okay, and try to solve this until you get this equation, this answer. And finally, I got two current, ID1 and ID2. So this is the value, 1.8 milliampere and 1.42 milliampere. At this time, we don't know yet which one is the IDQ, because we have to insert this value into the VGS equation. Remember that this VGS equation is equation number 2. Okay, so insert one by one for VGS1 and another one VGS2. So you insert here ID value for ID1, and this is for ID2. Okay, for the VGS1 here, we get VGS1 equal to 2 volt and VGS2 equal to 5.8 volt. So now we have to compare VGS1 and VGS2 with VGSTH. Why we must compare? Okay, remember the graph, okay, for this E MOSFET. Okay, for the E MOSFET, okay, the graph is at the positive side, because you see this is positive and the VGS is positive. So this graph is like this. Okay, so the transistor is on when the VGS value greater than the VTH. Okay, before the VTH value, less than VTH value, is the off condition, and here is on condition. So make sure your VGS is greater and is bigger than the VTH, then we can say that the transistor is on. So now we compare, the VGSTH is 4 and VGS2 now is bigger than the VTH. So I say that VGSQ is the from VGS2, 5.8 volt. So see here, VGS1 is 2. So this is not the VGSQ. So therefore, the ID2 and VGS2 now become the Q point value. Okay.